Hello, am I audible? Hello, is my voice audible?
Yes, sir.
Yes, sir.
Okay. Okay, so basically, you might have got the notice regarding the examination, means form fill up or whatever it is, and the internal exam is next week, but the total semester classes, okay, most probably it will be conducted till 12th. That is why I will be taking, I will be, we have to complete the syllabus within that. Okay, so let us see how far we can go. Okay, so that is why I have thought that I would discuss few numericals, but I think I have to cover the main theory part also before time, because next week we will not get any time for classes for the internal exam. Okay, so that is why when I will be teaching, one second. Okay, so in this lecture, since you have some basic idea about the electrostatics, so my pace will be a little bit higher. Okay, if you feel any, if you feel anywhere you are unable to understand, then you can tell me. Okay, or else I will be, covering the portion as much as possible. Because not only that, I will keep in mind that I will obviously concentrate on those topics which are new to you, but the topics which are already known to you, I will not spend too much time on those topics. Okay. For example, this equation we have already discussed, that B equals to mu H. Okay, value of mu and flux, it is already known to you. So like this, so I will not spend too much time in this, like this, in those areas. The areas which is unknown to you, that I will concentrate more. Okay. Okay, so this is the up to here we have discussed in the last class. Okay, so yes, so the discussion was that the flux, the electric flux is equals to the electric charge, which we know from the, from the Gauss law. Okay, now the difference between the electric flux and the magnetic flux is that electric fluxes do not converge in a particular point, it diverges. But magnetic fluxes converge at a particular point. When it starts from north pole, it ends at south pole. Okay, so that means the magnetic flux, the overall flux, okay, which is coming out, that is which is coming out. Suppose this is one flux. Okay, this is one flux over here. It is having some value. Okay, phi 1. This is another phi 2. Okay, so wherever may be different, because the fluxes which are closer to the poles have higher density, higher magnitude, which are away from the poles, they generally have lower magnitude. Now, if you take this integral, surface integral, okay, that means a closed surface, what will be the flux? In Gauss law, we have seen that the closed surface, the flux is equals to the charge. But in magnetic field, the magnetic fluxes, if you take the closed line integral of the flux density, closed surface integral, it will be 0. Why? Because in magnetic field, the fluxes do not come out of a box. Suppose you keep a magnet, and if the magnetic range of the bar magnet is within the box, if it is a stronger magnet, then the magnetic field will go outside. If you bring any iron material outside the box, it will get attracted towards the box. But if the magnet is not that powerful, the magnetic field is within the range of the box, then you will see that you will not find any flux coming out. But in electric flux, what happens? The fluxes come out all the time, because it is not converging at a point, it is continuously diverging and going outside. So the total fluxes coming out is equals to charge. But in magnetic field, the total flux which is coming out, okay, in a closed surface, it will be zero, because whatever flux is coming out from North Pole, it is ending at South Pole. Okay, that is why it is written over here that the closed surface integral of the flux density it will be equals to zero. Flux density of the magnetic field, okay, magnetic charge. Okay, because this is the main reason that you cannot isolate a North Pole from a South Pole. If you divide the magnetic poles, you will see at every how much division you make, you will always see the North Pole or South Pole are separated. And not we are unable to separate them. They are not separated, because if you divide the bar magnet at 1,000 pieces or a very tiny pieces, every piece will have a North Pole and South Pole. Okay, this is the nature of a magnetic pole. Similar for a electromagnet also. Okay, so that means the isolated magnetic charge does not exist. So this is the reason we are getting this equation. Now that means this closed surface integral is zero. Okay, but closed surface integral of an electric charge is not zero as per the Gauss law. Although the magnetostatic field is not conservative, magnetic flux is conserved. Now if you apply the divergence theorem, okay, you take this equation and you apply the divergence theorem, okay, so you take this equation, you apply the divergence theorem. Divergence theorem means the conversion from a volume integral to a closed surface integral. Okay, so here what we are doing, divergence theorem means that this is the closed surface integral. We can convert it into the divergence of surface volume integral of divergence of the vector. That means the closed surface integral of any vector can be represented as the volume integral of divergence of that vector. Now if you convert this, then what we can do, if this is equals to 0, then this will also be equals to 0. And this is the volume integral of divergence of B is 0. That means divergence of B is 0. This is one rule or law, you can say. Okay, this is one of the equations where it states that divergence of the magnetic flux density is 0, but it is not equal for electric flux density. Okay, only for magnetic flux density. This is the fourth Maxwell's equations. Okay, that the divergence of B is 0. So this is the, you can say this is the differential form of the Maxwell's equation. Integral form of the Maxwell's equation is this. This is the integral form. If it is asked what is the fourth Maxwell's equation in integral form, then you will write this equation. But for the differential form, we have to write this equation: divergence of B equals to 0. Okay. Now Maxwell's equation for static electromagnetic fields. So you can see this particular table. Okay, so I am not going to this discussion because it is already being explained, so I will explain this table. So these are the differential form. First column, you can see this is the differential form. Next column, it is the integral form, and these are the laws from which it is being derived. Okay, now Ampere Circular Law we have already discussed. Okay, so this is one equation which we have got from Gauss law, the first one, that is the divergence of D is equals to rho V, that is the volume charge density. From where we have got this? We have got this from Gauss law and from this integral form. Okay, In integral form, we have seen that the closed surface integral of d is equals to the volume integral of rho v. Okay. Now, similar thing, if you see these two equations are being paired. This is one equation. This is one pair of equation. This is one pair of equation. Right. This is for the electric field. These two. 1 second. Okay, so these two are for the electric field and these two are for the magnetic field. Okay, these two are for the magnetic field. Try to join the class within time. Okay, now why these two are paired? Because these two expressions are very similar to each other. You can see here also we are taking the divergence of the flux density. Here also we are taking the divergence of the flux density, but this here it is the flux density of the electric field. This is the magnetic flux density. So divergence of the electric flux density is equals to volume charge density, rho v. This is one Maxwell's equation. The next Maxwell's equation is that the divergence of the magnetic flux density is equals to 0. The third one is the, okay, so this equation where we have got, just now we have seen that this equation comes from the conclusion that the non-existence of magnetic monopole. That means a single magnetic pole do not exist. Magnetic poles exist in pairs. Okay, so now the third one is the curl of E is equals to 0. Where we have got this? We have got this in the expression or in the situation, if you can remember, that if you have a equipotential surface, a surface where the potential are equal everywhere. So if you take 2 points on the same surface, suppose point 1 and point 2, so potential at point 1 will be equals to potential at point 2. Okay, so potential difference between the 2 points in equilateral surface is 0. Okay, so V is equals to minus integral of E into dl. Okay, so the closed line integral of electric field intensity is equals to 0. From there we have got, using the Stokes theorem, that curl of E is equals to 0. That means the conservativeness of the electrostatic field. The electrostatic field is conservative. That we have concluded. Similarly, we have also seen an expression using the curl of magnetic field intensity, because this is the electric field intensity, this is the magnetic field intensity. We have seen from the Ampere Circular Law that the curl of H, magnetic field intensity, is equals to the current density. Okay, so here what we can see in electric field, the curl of a vector electric field intensity is 0, but curl of the magnetic field intensity is not 0, it is equals to J. Okay, where we have got this equation from the Ampere's law, circular law. So these are the Maxwell's equations for the static electromagnetic field. For the static, why? Because when the field is not static, it is dynamic. When it is moving, oscillating, then there will be some minor changes, addition to these equations that we will be seeing later on. Okay, so now going to the next topic, that magnetic field and magnetic static and vector potential. Now magnetic means we are talking about the magnetic potential. Okay, magnetic static and vector potential. So electric potential we all know. Okay, that is E electric field intensity is equals to negative of gradient of V. V is a scalar, so gradient of V. This was the expression of the relationship between the electric potential and the electric field intensity. Because electric field intensity exists, magnetic field intensity also exists. Electric potential exists, but magnetic potential physically we cannot define. Okay, so what we do, we assume that there must be some magnetic potential. Okay, it is not very similar to electric potential, because electric potential is different, because electric field, the electrons flow or charges flow, or the force between the two charges is very different compared to the force between the two magnetic poles. Okay, they are very different. So that is why the potential concept cannot be established in the same way as we have seen for the electric field intensity. But for the electric field, actually, electric field intensity and magnetic field intensity are very much similar to each other in their own periphery. But magnetic potential cannot be explained in that way. So what is done? We consider the magnetic potential exists, but we don't know what is the form of the magnetic potential. That is why we consider that magnetic potential can exist either in a scalar form or a vector form, because electric field intensity exists in a scalar form, because the electric potential exists in a scalar form. The V potential is a scalar, but magnetic potential can be a scalar or a vector. Okay, we will assume both of them. So in fact, the magnetic potential magnetic potential could be a scalar. Okay, suppose Vm or a vector A. So we will define magnetic potential scalar form as Vm and vector form as A, capital A. To define Vm and A involves recalling two important identities. Number one is that we know that curl of gradient of a scalar is equals to 0. Okay, these are the identities of divergence, curl and gradient. And divergence of curl of a vector is also 0 on any scalar field and a vector field. It is always common. Now, since in electric field intensity, if you concentrate on the electric field intensity, means we can see that electric field intensity is equals to the minus gradient of V. This is known to us. So electric field or electrostatic field, electric field intensity and potential are related like this. So similarly, we can define if magnetic field or in a magnetic field, if the potential is a scalar, because in electric field the potential is a scalar. So in magnetic field also the potential is a scalar. Suppose, then they should also have the same relationship. That is why we will replace E with H, electric field intensity with magnetic field intensity. Okay, then minus of gradient of the magnetic potential. We can consider this is only possible if the current density is 0. Otherwise, it is not possible. If the current density is 0, why? Because we know, as per the Maxwell's equation. Wait, let me go to the previous. Yes, in Maxwell's equation, you can see curl of H is 0. H is J. Okay, it is not 0. J is not 0. Okay, but if you take H equals to this, okay, that means J has to be 0. Okay, in that way.
तो सर इसका मतलब नॉन कंजर्वेटिव फील्ड्स का पोटेंशियल नहीं निकाल सकते?
नॉन कंजर्वेटिव, हाँ, नॉन कंजर्वेटिव फील्ड का नहीं, बेसिकली इसको कंजर्वेटिव समझ रहे हैं, ठीक है, इसको ये वाला, ठीक है, इसको ये कंजर्वेटिव नहीं है. इलेक्ट्रिक फील्ड इंटेंसिटी, व्हाई वी आर टॉकिंग अबाउट दिस, बिकॉज सी द रिलेशनशिप इन इलेक्ट्रिक फील्ड इज इक्वल्स टू माइनस ग्रेडियंट ऑफ वी. ठीक है, अब मैग्नेटिक फील्ड में ऐसा रिलेशन नहीं है, इसलिए ही देखो इसके साथ रिलेशनशिप अलग है. ये देखो यहाँ पर इलेक्ट्रिक फील्ड में क्या था, इलेक्ट्रिक फील्ड में कर्ल ऑफ ई 0 था, ठीक है, लेकिन मैग्नेटिक फील्ड में कर्ल ऑफ एच, मैग्नेटिक फील्ड इंटेंसिटी इज नॉट 0, इट इज जे. लेकिन अगर हम लोग ये मान लेते हैं कि इलेक्ट्रिक फील्ड जैसा ही मैग्नेटिक फील्ड है, ठीक है, तो इलेक्ट्रिक फील्ड में क्या है, E इक्वल्स टू माइनस ग्रेडियंट ऑफ V. अभी मैग्नेटिक फील्ड में ऐसा नहीं है, लेकिन हम लोग जबरदस्ती मान रहे हैं, ठीक है, मैग्नेटिक फील्ड में भी एक स्केलर पोटेंशियल है जो है Vm. मैग्नेटिक फील्ड Vm मतलब मैग्नेटिक फील्ड, मैग्नेटिक पोटेंशियल. तो अगर हम ये एस्टेब्लिश करते हैं तो ये भी मानना पड़ेगा कि ये 0 है, जैसे कि इसके लिए है, नहीं तो ये एस्टेब्लिश नहीं होगा. That is why we are considering the magnetic field to be conservative also. That means for a conservative field is not possible, but if theoretically, if the magnetic field is conservative, then only we can establish that there exists a potential in magnetic field also which is scalar, similar to electric field. Similar to electric field also, magnetic field में भी एक पोटेंशियल है जो स्केलर है, इलेक्ट्रिक, ठीक है, वैसा। इसलिए हम लोग इसको भी मान रहे हैं कि ये भी जीरो है। Okay, so if J is 0, then only we can have this equation, otherwise we cannot have this. So the condition attached to this equation is important and will be explained. Combining equation number 2 and this expression of curl of H equals to J, जो हम लोग जानते हैं ऑलरेडी एक्चुअली एग्जिस्ट करता है, ठीक है। तो कर्ल ऑफ H इक्वल्स टू J मतलब J इक्वल्स टू कर्ल ऑफ H, और H को हमने सोचा है कि H इक्वल्स टू माइनस ऑफ ग्रेडियंट ऑफ Vm, वो लिखा है हमने H की जगह पे। लेकिन हम लोग ये भी मान चुके हैं कि J जीरो है, इसलिए ये पूरा जीरो हो जाएगा। अभी ये देखो, ये चीज, ये क्या कर रहे हैं हम लोग, मतलब कि उल्टे दिशा से हम लोग प्रूफ कर रहे हैं कि यहाँ पर देखो कर्ल ऑफ माइनस ऑफ ग्रेडियंट ऑफ अ स्केलर, ऑलरेडी पता है कि कर्ल ऑफ माइनस ऑफ कर्ल ऑफ ग्रेडियंट ऑफ अ स्केलर जीरो होता है। ये यू कैन से दिस इज द कॉमन रूल, ओके, एंड आइडेंटिटी ऑफ द वेक्टर। ये दो आइडेंटिटी है वेक्टर का, ठीक है। अभी सेम आइडेंटिटी देखो यहां पर भी प्रूफ हो रहा है, तो इसका ये मतलब है कि हम लोग अगर कर्ल ऑफ ग्रेडियंट ऑफ अ स्केलर लेते हैं तो हमेशा जीरो ही होगा, ठीक है, ये जीरो होगा। तो क्या करेंगे, इसको मैग्नेटिक पोटेंशियल हम लोग समझ सकते हैं, कंसीडर कर सकते हैं, लेकिन तभी कंसीडर कर सकते हैं जब हम लोग ये मान लेते हैं कि जे का वैल्यू जीरो है, तब ये एग्जिस्ट करेगा, ठीक है। दिस इज द assumption. So thus to satisfy the condition, thus the magnetic scalar potential Vm is only defined in the region where J is equals to 0. So that means magnetic potential exists in the scalar form only in the area where the current density is 0. Otherwise magnetic potential will not exist in the scalar form. This is the conclusion. We should also note that Vm satisfy Laplace equation just V does for electrostatic field, ठीक है। जैसे इलेक्ट्रोस्टैटिक फील्ड में हम लोग ने देखा है कि लैप्लेस इक्वेशन, दैट मीन्स डेल डेल स्क्वायर ऑफ स्केलर जो होता है वो जीरो हमको मिला था। तो अगर जे जीरो है तो मैग्नेटिक पोटेंशियल के लिए भी सेम होगा, ठीक है। अभी क्या करेंगे हम लोग, ये एस्टेब्लिश हो गया कि अगर मैग्नेटिक फील्ड में अगर कोई पोटेंशियल, इफ द पोटेंशियल इज इन अ स्केलर फॉर्म, इफ वी एज्यूम, देन it will be only possible where J is 0. This is the conclusion, okay. Now we will consider that if the magnetic potential is a scalar, अब magnetic potential अगर scalar है, vector is a vector, then what will the expression? Now in this case we cannot relate with the electric field, because in the previous case we have related to the electric field and we have taken the same example or same equation and we have just copy pasted, just replacing the electric field intensity with magnetic field intensity and electric potential with magnetic potential. So this conclusion was coming. So this was the condition, okay. But when we are considering the magnetic field, that potential exists in the magnetic field in vector form, so we cannot relate with the electric field because we don't have a reference, okay. So what we can do, we will assume that, see, divergence of B is 0, that we have got, okay, because of the magnetic monopole do not exist. Now B can be represented as curl of a vector, okay. That means if any vector whose divergence is 0, okay, that means it can be expressed that the vector is equals to curl of any other vector, okay. It can be expressed, it may be a curl of a vector, हो सकता है, क्योंकि डाइवर्जेंस और कर्ल का क्या रिलेशन है, रिलेशन बेसिकली होता नहीं है कुछ। डाइवर्जेंस मतलब क्या, ये जो एक पॉइंट है यहाँ पर क्या हो रहा है, डाइवर्जेंस हो रहा है, ठीक है, हम लोगों ने देखा है पहले, ये पॉजिटिव डाइवर्जेंस है, अगर अंदर की तरफ जा रहा है तो नेगेटिव डाइवर्जेंस है। कर्ल मतलब कोई वेक्टर अगर ऐसा घूम रहा है तो उसको कर्ल कहते हैं, ठीक है। अगर कर्ल होके किसी पॉइंट से निकल रहा है तो वो डाइवर्जेंस कर्ल दोनों ही पॉजिटिव है। जैसे कि ये वाला, इसका डाइवर्जेंस कर्ल दोनों ही है, डाइवर्जेंस भी है कर्ल भी है। लेकिन इसका डाइवर्जेंस नहीं है, लेकिन कर्ल तो हो सकता है ना, इट कैन बी, देयर कैन बी अ कर्ल। ओके, दैट ऑल्सो वी हैव सीन इन द प्रीवियस लेक्चर्स। ओके, मैंने पीपीटी भी भेज दिया है। तो अ कर्ल कैन एग्जिस्ट, so that means B is the curl of a vector, suppose vector A. okay, अभी वेक्टर A क्या है? A है magnetic potential in vector form. We are assuming that the vector, if it is a magnetic vector, if it is a magnetic potential if is in vector form, then it will be equals to curl of flux density, curl of magnetic flux density B. Okay, that we can assume, because we cannot establish, just we are assuming that for theoretically that B is equals to curl of A. Now we know that if a potential is expressed, okay, in the integral form, then how it is coming, where the potential is coming from? The potential is coming from the charge, because potential means the force experienced, that means the work done to move a positive charge from one point to another, or infinity to a particular point. There is a potential at that point, and the work done to bring a point from one point to another, charge from one point to another, that is the potential difference between the 2 points. Now we are talking about the potential. So potential means from infinity to a point we are moving a charge, and the distance is r. Similarly here also, we are moving one magnet from infinity to a particular point, and that magnet is not a bar magnet, that magnet is a current element. करंट एलिमेंट मतलब ये जो कंडक्टर है उसमें आई करंट जा रहा है, ठीक है। कंडक्टर का जो टोटल लेंथ है वो है एल, लेकिन लोग छोटा सा हिस्सा लेंगे, छोटा जैसा हिस्सा है ये वाला, मान लो कि ये छोटा सा हिस्सा है डी एल, इससे करंट आई एल ही है, तो ये वाला जो है करंट एलिमेंट ये होगा आई डी एल, सिमिलर टू ए इलेक्ट्रिक चार्ज, दिस इज अ करंट एलिमेंट। ओके, इसको हम लोग इलेक्ट्रिक चार्ज की तरह मैग्नेटिक चार्ज जैसा ट्रीट करेंगे, we'll treat it like a magnetic charge, so it is a current element. We have already seen in Ampere Circular Law. What we will do, we will replace dq with IDL. Okay, the mu IDL, mu because there is some permeability in the material, नहीं तो मैग्नेटिक फील्ड नहीं होगा ना, मटेरियल में परमेबिलिटी होना चाहिए, क्योंकि एक मटेरियल में करंट फ्लो कर रहा है। इफ अ करंट इज फ्लोइंग इन अ कंडक्टर, इट इज क्रिएटिंग अ मैग्नेटिक फील्ड, दैट मींस देयर इज सम परमेबिलिटी आल्सो, that is why we have represented as mu IDL by 4 4 पाई आर, क्योंकि यहाँ पर परमिटिविटी डिनोमिनेटर में, यहाँ पर परमेबिलिटी कंडक्टर के साथ है इसलिए ऊपर होगा, और यहाँ पर क्या, यहाँ पर था परमिटिविटी जो था, परमिटिविटी एनवायरमेंट के ऊपर डिपेंडेंट था, दैट इज व्हाई इट वाज इन द डिनोमिनेटर, बट ओवर हियर द परमिएबिलिटी इज रिलेटेड टू द कंडक्टर कोर, दैट इज व्हाई इट इज इन द न्यूमरेटर। Same thing we can represent in the surface current also, line current, or we can represent in the form of surface current or the volume current. इसका भी ट्रांसलेशन हमने देखा है, ट्रांसफॉर्मेशन देखा है हमने, that is why I will not repeat it. So this is the vector form. That means if the magnetic potential exists in the vector, then it is the curl of a magnetic flux density, and A can be represented in this form. Okay. Okay. So rather. Then obtaining equation number 7 to 9 from equation number 6, an alternate approach is that we can also represent in this way also, that the equation of H that we already know, the equation of the flux density. Okay, equation of the flux density means यहाँ से हम लोग ये जो एक्सप्रेशन था ये दिखा दूंगा तो इजी होगा। वेट, yes, this equation, Ampere Circular Law. Okay, Ampere Circular Law was there. Second. this equation, if you can remember. Okay, so this is the equation of the magnetic field intensity. Okay, magnetic field intensity. So same thing. Okay, magnetic field intensity. Now, if you want to replace, or you can represent in the form of the electric, or you can say, sorry, magnetic vector. Okay, so that means if this is B, H, okay, so H and B, the relationship we all know. From H we know that how to represent B, because B is equals to mu H. तो यहाँ पर हमने ये इक्वेशन को लिया है, तो यहाँ पर म्यू को मल्टीप्लाई किया है. ठीक है, यहाँ से हम लोग A को भी निकाल सकते हैं. क्या करेंगे, ये जो B का वैल्यू है, B जो वेक्टर है, इसको क्या करेंगे हम, दिस इज इक्वल्स टू कर्ल ऑफ A इज इक्वल्स टू B. ओके, दैट मीन्स इट इज सम वैल्यू ऑफ कर्ल ऑफ A. ओके, so from there we can relate this equation. Okay, so this is just the derivation. So main important part is this one. This is the important part. अगर question आता है कि what is the form of magnetic potential in vector, or how to represent the magnetic potential in vector form, then you have to establish this equation. Okay, and you have to write that A is equals to, can be considered, if it is a line current, then can be represented in this form. If it is surface current, then this form, volume current, so this form. Okay. Now these are the just the you can say the expressions. Okay, so these do not generally, the derivations do not come, just for your understanding. So I will just come to this conclusion, जहाँ पर पोटेंशियल का एक्चुअल एक्सप्रेशन लिखा है, वहाँ तक मैं जा रहा हूँ. ठीक है, यहाँ पर देखो, फ्लक्स जो है, मैग्नेटिक फ्लक्स का इक्वेशन क्या है, सरफेस इंटीग्रल ऑफ बी. ओके, सरफेस इंटीग्रल ऑफ बी. इसको हम लोग अगर स्टोक्स थ्योरम अप्लाई करते हैं, स्टोक्स थ्योरम मींस ट्रांसफॉर्मिंग अ सरफेस इंटीग्रल टू अ क्लोज लाइन इंटीग्रल. तो फ्लक्स, मैग्नेटिक फ्लक्स इज इक्वल्स टू सरफेस इंटीग्रल ऑफ फ्लक्स डेंसिटी. नाउ बी इज इक्वल्स टू, वी हैव कंसीडर्ड बी इज इक्वल्स टू कर्ल ऑफ ए, जो अभी देखा हमने कि मैग्नेटिक पोटेंशियल अगर वेक्टर में है तो बी इक्वल्स टू कर्ल ऑफ ए. तो ये इसको ट्रांसफॉर्म किया है. तो स्टोक्स थ्योरम का मतलब क्या है कि एक वेक्टर जो कर्ल है, कर्ल जो सरफेस इंटीग्रल में है, उसको हम लोग क्लोज लाइन इंटीग्रल में ट्रांसफॉर्म कर सकते हैं. तो ये वाला जो इक्वेशन है, ये एक साथ है, इसको हमने ट्रांसफॉर्म किया है, इस वाले में ट्रांसफॉर्म नहीं किया है, जस्ट लिखा है, रिप्लेस किया है बी को ए में. अभी स्टोक्स थ्योरम में ट्रांसफॉर्मेशन ये हमको मिला है, तो इसको हम रिप्लेस करेंगे इससे. तो क्या मिला, अभी फ्लक्स जो है वो सरफेस इंटीग्रल था, अभी लाइन इंटीग्रल हो गया, तो लाइन इंटीग्रल ऑफ ए निकल गया. सो दिस इज द इक्वेशन ऑफ फ्लक्स विथ रेस्पेक्ट टू द मैग्नेटिक पोटेंशियल ऑफ वेक्टर फॉर्म. तो दो इक्वेशन निकल कर आता है कि B इज इक्वल्स टू कर्ल ऑफ ए. If the magnetic potential exists in a vector form, then it will be curl of A. And flux का जो है वो क्या है, अगर ये फ्लक्स डेंसिटी मतलब क्या, फ्लक्स पर एरिया. ठीक है, फ्लक्स पर एरिया. तो फ्लक्स क्या है, फ्लक्स का रिलेशन होगा ऐसा, लाइन इंटीग्रल ऑफ ए. ठीक है, दिस फॉर्म इज नॉट, वी कैन नॉट सी इन दी इलेक्ट्रिक फील्ड, बिकॉज इन इलेक्ट्रिक फील्ड दी पोटेंशियल इज स्केलर. But in vector form, in magnetic field, it will have a new relationship with respect to flux. ठीक है. Okay. So thus the magnetic flux through a given area can be found using this particular equation we all know. So also the magnetic field can be determined using Vm or A. The choice is dictated by the nature of the given problem, except that Vm can only be used in a source free region. Source free region क्यों, क्योंकि J equals to 0 होगा. अगर मैग्नेटिक पोटेंशियल को स्केलर मानते हैं तो वो तभी हम लोग अप्लाई कर सकेंगे जहां पर सोर्स नहीं है, where the value of the current density is 0, J is 0. But where we have the value, where the vector, where the potential is a vector form, in that case there has to be source, because in this case j is having a positive value, or you can say a particular integer. Okay, it is a non-zero value. Then if it is a non-zero value, then if it is told that there is a source in the system, the source is non-zero, the current density is non-zero, but you have to find out the magnetic potential, then your answer will be yes, then the magnetic potential will be vector. Okay, the use of magnetic vector potential provides a powerful, elegant approach to solving electromagnetic problems, particularly those relating to antennas. So electromagnetic field means related to the communication signals. Okay, and not only communication signals, in transmission line also the electromagnetic property is observed, because in electric current, when it passes through a high voltage, electromagnetic wave is observed. So theoretically, this particular case of vector potential of magnetic field have to be considered for calculation. तो ये calculation purpose के लिए बहुत important रहता है vector potential A magnetic field के लिए, ठीक है. So this one numerical. Okay, it shows that it tells that given the magnetic vector potential A, which is equals to minus rho square by 4 unit vector z, that means it is along the z axis. It is a vector, so it is along the z axis. Unit is Weber per meter. Okay, Weber per meter क्यों? क्योंकि यहाँ पर देखो फ्लक्स जो है वो लाइन इंटीग्रल ऑफ ए है, ठीक है. यहाँ पर रिलेशन क्या है? फ्लक्स इक्वल्स टू ए इंटू लाइन इंटीग्रल लेंथ. तो ए क्या होगा? फ्लक्स बाई लेंथ, so Weber by meter. That is what is called Weber per meter unit. ठीक है, ठीक है, Weber per meter. So this is the equation, or sorry, this is the unit. This is the reason why the unit is Weber per meter. So calculate the total flux across the surface. Which surface? Across this surface where phi is equals to pi by 2. Rho is from 1 to 2 and z is from 0 to 5. That means rho phi z. That means what we can understand that this particular coordinate system is the cylindrical coordinate system. Okay, so this is a cylindrical coordinate system. So now there are two methods of solving this. What we have to find out? We have to find out the total flux phi. We have to find out this flux. We have to find out. Now B is equals to curl of A. Now A is given. You have to find out the curl of A. Okay. So curl of A means we all know how to find the curl. It is a cross product. So cross product with the del operator with the vector that we know. So our solution is rho by 2 that we can work out. कैसे करना है? अगर याद नहीं है तो कर्ल ऑफ ए मतलब ऐसा होगा कि कार्टेशियन कोऑर्डिनेट में जो हमने देखा है, ठीक है. ठीक है, और यहाँ पर जो वेक्टर होता है ए एक्स ए वाई ए जेड, इसको कर्ल होता है, डिटरमिनेंट निकलता है, ठीक है, उस हिसाब से. तो वैसे करना है, ठीक है. तो जब सिर्फ z का टर्म होगा, ठीक है, तो आवर कंक्लूजन विल बी बिकॉज z with respect to, I think it is rho, because rho is there and z is there, so cross product will give you the unit vector of phi axis. Okay, now area is in the rho axis and the z axis. Okay, now hence the flux will be surface integral of B. So B तो निकल गया है, ठीक है, S भी निकल गया है, तो इसलिए हम लोग को फ्लक्स का वैल्यू निकल जाएगा, ठीक है. ये मेथड 1 है. तो फिर से रिपीट करते हैं. B मतलब कर्ल ऑफ A. A is given, so you have to find the curl of A, so you will get this value.
Share your screen, sir.
हाँ?
Share your screen, sir.
स्क्रीन, अच्छा, आई थिंक नेटवर्क प्रॉब्लम की वजह से स्क्रीन चला गया. ठीक है, मैं कोशिश करता हूँ फिर से. I think there is a problem in the browser. Well, let me exit. So this was the problem. So the magnetic potential in vector form is given. So you have to find out the flux. Okay. So our flux we have to find out the flux density first. So B is equals to curl of A. So by using the curl, by taking the curl of A, we will be able to determine the value of B, which is in the phi axis. Okay. Now, since it is in the phi axis, so the curl is taking place between rho axis and z axis. So that is why the surface integral will be for the rho axis and z axis. Okay. So the ds, value of ds will be along rho and z, and the cross product of these two will give you the resultant unit vector to be in the phi axis. So that is why it is resultant vector is phi. We will take the surface integral. Okay, so first of all, z axis means it is from 0 to 5, and rho is from 1 to 2. Okay, and if you integrate, you will get the solution of flux. This is method number 1. Method number 2 is, if you see, this is the application of method number 2, where we will add the fluxes. So in method number 2, we use that this equation. We are not using the curl of A. We are directly using this equation. There is a line integral of A, vector potential. So see this expression, this approach is little bit different. Okay. So where we are using the relationship between the magnetic flux and the vector potential. Okay. In the magnetic potential in vector form. So curl of surface, the closed line integral of A. That means we will integrate the potential at every point. Okay, so what will be the flux at this point, we will calculate, then at this point, then we will add them all. Okay, So where L is the path boundary of S. Okay, so phi 1 to phi 4, 4 parts we have taken because there are 4 sides. Okay, so now since A has only Z component, because A has only Z component, so we are writing in this form, because A has Z component, because it is already mentioned in the question that the vector is in the Z axis. Okay, Z component only. So since A has only Z component, so phi 1 and phi 3 will be 0. So phi 1 and phi 3 will be 0 because the potential only exists in the Z axis. So Y axis will not exist. Suppose if you take the Cartesian coordinate system or whatever, if you take the cylindrical also, then also only Z axis will be existing. So we have to find out the potential at line this particular part 2 and part 3. Okay, if you take the total flux at part 2 and part 3, we will add them, we will get the total flux. Okay, so you have to just find the integral. So the solution will be, you can see it is the solution, we are taking minus 1 by 4 common. Why? Because in the Z axis it is from 0 to 5. Okay, from 0 to 5, this part, and this part it is from, you can see this is from 1 to 1 second, row is from 1 to 2, row is from 1 to 2. Okay, so 1 to 2 means this is, suppose row, this is not Z Y axis, actually this is row, this is row. So row is from 1 to 2, so this is 0, this is 1, and this is 2. So it exists between 1 and 2. Okay, that is why we are taking this as 1, first one is 1 and this one as 2, because this part is having the gap of 1 unit and this number 4 is having a gap of 2 unit. That is why we are taking the row to be 1 and 2 respectively, and Z axis from 0 to 5. Now if you integrate, we will get this solution. Okay, as previously, we can obtain this solution for flux by using both the magnetic flux density, that is B equals to a curl of A, or by using the new relation that we have just learned, that flux is equals to the closed line integral of A. Either of the two, if we apply, we can get this same solution. Okay. Okay, so I am ending my lecture over here because it is already time. Okay, so we will after the internal we will continue with the next topic. Okay. Okay, so then thank you, students.
Thank you, sir.